Have you ever wondered how to group similar things together? For example, grouping similar tweets or text messages? Well, that's what we're going to do this time around. We're going to look at how to think about the problem, what data structure arises from the reasoning, and what algorithm we can use to compare the text together. There are many variations of this problem, and what you see in websites like Twitter can be very sophisticated. What we are going to create here is a simplified version, but nevertheless useful. Let's look at the problem. What is similarity? Let's start with a simple example. We can take a random group of people and look at their heights. People with similar heights tend to be close together when we draw the heights on a graph. Here's x-axis that represents the height, and we put a dot each time we measure a height. You see that people with similar heights are clumped together here. And let's add another measure, this time the weight. We can assume this measure is independent for this example and add as another axis y. So now we can draw a two-dimensional chart and plot like this. And when you have enough data, you will start seeing groups like this. Let's add yet another measure, number of steps they walk on average every week. We can add this to the z-axis and again plot this as a 3D chart. With large enough data points, you'll again start seeing the groups of similar people. So the intuition here is that we can select a number of dimensions or metrics we can measure, and when we plot them all in a graph, we should see similar items clumped together based on those metrics. With this knowledge, let's see if we can implement an algorithm to group similar items of text like tweets. The inputs to this algorithm would be two sentences, and it should return a value telling us how similar they are. So the similarity is easily understood as a value between, for example, 0 and 1. 1 being almost identical and 0 being completely different. So let's see how we can quantify various measures of data items so we can operate on them. In our example of people's attributes, we had height, weight, and number of steps. All these are numerical values, and we can describe a person with these three properties. So we can write them like person 1, weight, height, steps, person 2, weight, height, steps, and so on. So as you can see, we can represent each data item as an array of numerical values. Each slot of the array represents a value in a different dimension. In mathematics, this is called a vector. Now let's do simple trigonometry here. We can draw a two-dimensional vector like this as a line. Here's the x-axis and here's the y-axis. And this vector has, for example, values 1, 1. We can plot these in a graph like this, and we can compute a few things. We can compute the size of the vector. This is called the magnitude. That is given by its length. And we can take the length by the simple Pythagoras formula z squared equals x squared plus y squared. And angle between the x-axis and the vector is given by the basic trigonometry cos t equals adjacent divided by hypotenuse. These two things will come in handy in a bit, so I'll let it marinate. Now let's look at two vectors that are close together. We can draw them like this. Obviously, two vectors that are close together has a smaller angle between them than the ones which are far apart. Now, if you remember from the previous charts we drew, the things that are similar tends to be closer together. What that means is when we represent these items as vectors, the angle between them tend to be smaller. Now, we have a way of measuring similarity with one number, the angle between the vectors. With basic trigonometry, we can compute the cosine between two vectors like this. Cosine of an angle varies between -1 and +1. So our measure of similarity has bounds between these two values. So we can derive this from basic trigonometry and Pythagoras theorem. This is not mathematically rigorous method, but it will show you how a formula can be constructed so that we can compute cosine of the angle between the two vectors. So what we discussed so far about vectors can be implemented in the code like this. It has only a few lines. Here in the constructor, we create a vector object with a list of numbers passed in. This operator is called an indexer, and it allows us to get elements with an index. Here's the dot product method. It is a matter of iterating the elements and multiplying them and adding to an accumulator called sum. Here's the magnitude method. It creates a magnitude using the dot product and take the square root of it. Now we come to the cosine function. Here, as we derived earlier, we take the dot product of the vector b passed in, divide that by the product of the magnitudes. Don't worry too much if you don't understand this part. This is basic trigonometry, and you can read more about vector math and algebra if you want to learn more. We validate this class with a few tests like this. Now that's out of the way, we can think about how to measure the similarity between the tweets like this. Here's a test covering that case. If you look closely, these two lines are very similar, and it should get a high score. Also, these two lines. Now, these two lines, time for pizza and I like cheeseburgers, talk about food, but they are not that similar. So it should get a lower score. The last pair has no relation, so it should get a low score. Now the challenge is, how do we create vectors out of these text phrases? In machine learning, there are sophisticated ways of capturing the properties of language, like the semantic similarity and such. But here we're going to do something very simple. So here are the things that we can do out of the box. We can count the number of words in a sentence. That would be our first metric. Then we can convert each character into an integer and add them together and average it. So with that, we capture the nature of characters used in the phrase. Another metric you could use is the length of a phrase, which is very easy. And also, we can create a histogram that would give us the distribution of frequencies of each letter in a phrase. As you can see, we are using very mechanical properties of language. We don't measure any kind of a semantic property, so our similarity metric will not perform well on meaning of the words. It's important we understand the limitations of our algorithms so we know how to use them. There are no universally good algorithms. We optimize for some properties we can live with. Okay, enough talk, show me the code. Here we are in the class called Similarity. Here I am creating a dictionary of characters that maps to an index, just so that we can enumerate on a sentence and perform numerical operations on it. Remember, in computers, underneath all, they are all numbers, and then further below, it is Boolean logic. We are converting the text to lowercase, and we only care about the alphanumeric characters and the space. Here's our function to average character sum of a piece of text. It goes through each character and converts to a number, adds to the sum, and returns the average. So simple. So here, largest function of this class, that creates a histogram. Histogram is a simple mechanism of counting frequencies of various items. Here the items are characters in a piece of text. This gives an idea how many times a character in our dictionary appeared in the text. We iterate over the text, take each character, convert it to an index, and increment the count in that bin of the histogram. Here I am adding 10 each time I see it. By 10, well, why not? Experiment with any number you like and find one that fits your needs. And here's the public API that does the comparison job. It receives two strings and returns a number saying how similar they are. Computes the vector from each sentence, take the cosine between them, and that's it. So simple. Okay, so enough talk, show me the results. Here we go. Let's run the tests. The last one is not exactly a test, but allows me to compute similarity and print a number like this. So let's see how it performs. Comparing ABC with ABC gives a perfect score of 100%. Nice. Comparing DEF with XYZ returns 19%, which is low as it should be. Pacific Rim Trailer yada 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 has a 87%, which is a high score for the similarity, as it should be. Next tweet pair are very similar to each other, and that has 93%, and the next two pairs are similar as well, and they have high scores as expected. This pair, Chase All Your Cares Away and Forget Your Troubles, these two are semantically similar but otherwise not much in common, and our algo returns 60%, which is not bad. But our algo has no way to measure the meaning, so it will perform somewhat poorly here. Next pair is about food, but not much in common otherwise, and our algo gives 57% and can be explained by the lack of measurement or meaning. The last pair are not similar semantically or syntactically, and it should receive a low score, but our algo fails on it. So this little algorithm we created for measuring similarity works fine for a small data set, and it's kind of a toy algorithm, and it won't generalize for a wider case. When you have a smaller data set, you can create small algorithms like this. When you have a larger data set, you can create algorithms that learns from the data, like in deep learning or machine learning. Our algorithm is handcrafted and it doesn't learn from the data. We picked a random set of features we can quickly implement and got a decent result for that data we have. There's a lot we can do to measure similarity, and if you're interested in this, I could create more videos on machine learning related themes. Okay, so that's it for this video. Thanks for watching. As always, if you like what I create, please like, share and subscribe to the channel. Just a note, I decided to move the live stream to YouTube from Twitch. So the next Saturday morning at 10 AM UK time, I will go live and answer your coding questions. Until next time.